The title of this talk is Knapsack and the Power Word Problem in Solvable Baumslag-Solitar Groups. My name is Markus Lohrey. I will present the first half of the talk. The second half will be presented by my co-author Lohrey and Zetzsche. In this talk we will consider computational problems in infinite groups, but in order to be able to compute in an infinite group you need some restriction. And here we will consider the restriction of being finitely generated. So a group G is called finitely generated. We will use the abbreviation FG in the following. If there exists a finite subset sigma of so-called generators in the group G, such that every element of the group can be written as a product of generators and inverse generators. So in other words, this means that every element from the group can be represented by a finite sequence or by a finite word over this alphabet sigma union sigma minus 1. Now the most important computational problem in a finitely generated group is certainly the word problem. And it's defined as follows. So the input is a word W over this alphabet sigma union sigma minus 1, so over the group generators and their inverses. And the question is whether this word represents the group identity in G. So in other words, if you multiply the generators and inverse generators in W from left to right, you obtain the group identity. So the word problem was introduced by Max Dehn in 1910, and Dehn was actually interested in topological problems, and thereby he proved that the word problem is decidable for every two-dimensional surface group. Let me also remark that the decidability and also the computational complexity of the word problem does not really depend on the concrete generating set that you choose. Now in general, unfortunately, there is no hope for decidability. Novikov and Boone proved in the 1950s this famous result that there is a finitely presented group with an undecidable word problem. Where finitely presented means that the group is finitely generated and can be defined by finitely many so-called relators or defining identities. On the other hand, fortunately, there are many interesting and also natural classes of groups where the word problem is decidable and where you can also prove upper bounds on the computational complexity. Let me give you some examples. So Lipton and Salkstein proved in 1977 that a word problem for a finitely generated linear group, so a finitely generated group of matrices over a field, can be solved in deterministic log space. If you restrict to finitely generated linear solvable groups, then the complexity of the word problem goes down to d log time uniform TC0. So TC0 will appear later again, so let me give you some details. So TC0 is a circuit complexity class, and it contains all languages or all problems that can be accepted by a polynomial size Boolean circuit family of constant depth, where in addition to Boolean gates, you may also use threshold or majority gates. D-log time uniformity is a little bit technical. I won't define it here. It's the strongest reasonable notion of uniformity that you can actually require. And let me just say that D-log time uniform TC0 is actually captured by the complexity of multiplication of binary encoded integers. So a very natural problem, complete problem for D-log time uniform TC0 is the question whether a certain bit in the product of two binary encoded integers is 1. Another interesting class of groups are hyperbolic groups, which are very important in geometric group theory. For these groups, the word problem can be solved in linear time. This was shown by Gromov. And let me finally mention a famous result of Magnus from 1932. He proved that the word problem is decidable for every one relator group. So one relator group is a finitely presented group which is defined by a single relator or defining identity. The proof actually shows that the word problem is primitive recursive, but no much better general complexity upper bound is known. So there are many one relator groups where the word problem can be solved in polynomial time, but it's widely open whether for every one relator group the word problem can be solved in polynomial time. In this talk, we will consider a subclass of one-related groups, an important subclass, the so-called Baumslag-Solitar groups, which appeared as counterexamples in some group theoretic conjectures. And the definition is the following. Take two natural numbers, p and q, which are non-zero, and then you define the Baumslag-Solitar group B as PQ as the one-related group generated by A and T, and the single defining identity is T minus 1, A to the power of P, T equals A to the power of Q. So if you conjugate A to the power of P by the letter T, you obtain A to the power of Q. And Armin Weiss proved in 2015 that the word problem for every Baumslag-Solitar group can be solved in deterministic log space. In this talk, we will be even more restrictive. We will only consider Baumslag-Solitar groups B as 1Q. So the single defining identity is T, in the inverse of T, AT is equal to A to the power of Q. And the interesting thing about these groups is that they are solvable and linear. And they were studied in many other papers too. There is a very simple matrix representation of B as 1Q, namely it's isomorphic to the subgroup of 2 by 2 matrices over the rational numbers that are generated by these two matrices here. And since the word problem for every solvable, finitely generated solvable and linear group can be solved in d-log time uniform TC0, well, the same is true also for B as 1Q. So the complexity of the word problem is very low. It's the same as multiplication of binary encoded integers. Now in this talk we will consider two computational problems in solvable Baumslag-Solitar groups, and the first one is the so-called power word problem, which is a succinct variant of the word problem. So let me define the power word problem in general for a finitely generated group G. Let's fix a finite generating set sigma. And then the power word problem is defined as follows. So the input is a sequence of words W1 to WK over the generators and their inverses. And these words are written down explicitly. Moreover, we have binary encoded natural numbers N1 to Nk. And the question is whether this word here, so W1 to the power of N1, W2 to the power of N2, and so on, Wk to the power of Nk, whether this word represents the group identity in G. So the succinct point here is that, well, you can use these binary encoded exponents here, which allows you to write down very long words, assuming the words have repetitions in a succinct way. Let me remark that the complexity of the power word problem does not really depend on the generating set. So if you change the generating set, the complexity does not change substantially. This is also the case for the word problem, by the way. The power word problem is a special case of the so-called compressed word problem for G, where the input word is represented by a so-called string straight line program. And the power word problem was actually in the commutative setting, it was already considered by G in 1903. He proved that for given algebraic numbers alpha 1 to alpha k, which are represented or given by their minimal polynomials, and binary encoded numbers n1 to nk, one can check in polynomial time whether the number alpha 1 to the power of n1 and so on, alpha k to the power of nk is 1. Now let me also give some examples or some complexity results for power word problems for groups. So first of all, there are several interesting groups where the complexity of the power word problem is very low, d-log time uniform TC0. This is the case for finitely generated nilpotent groups as well as for free solvable groups. For finitely generated free groups as well as this famous Grigorchuk group, the precise definition is not important here. So for these groups, the power word problem can be solved in log space, deterministic log space. And for another famous group, the so-called Thompson's group F, the power word problem turns out to be co-NP complete. Now our first main result states that for a solvable Baumslag-Solitar group BS1Q, the Bauer word problem, belongs to D-log time uniform TC0. And the proof uses the matrix representation for BS1Q that I have shown you before. Let me give you some details. The main step is to reduce the Bauer power word problem for BS1Q to the following computational problem. So the input is a polynomial p in the variable x with integer coefficients a1 to ak here. But this polynomial is represented in a succinct way, namely it's represented by the list of coefficients a1 to ak and the corresponding exponents e1 to ek. And all these numbers here are represented in binary notation. So you can succinctly represent polynomials of very high degree in this way. This representation is sometimes called the supersparse or lacunary representation. And the question is whether the number q is a root of the polynomial p. So this is the main step, to reduce the power word problem for BS1Q to this problem here. Now, this problem about polynomials actually can be solved in polynomial time, and this result can be found in a paper by Lenstra from 1909. And actually Lenstra proved more. He proved this result for every algebraic number in place of the natural number q. Now, if you look at Lenstra's proof, it's not hard to observe that the algorithm can be actually implemented in D-log time uniform TC0. And this together yields theorem 1. But actually it yields more. Namely, we get the following result. Take any complex number alpha, non-zero, then the power word problem for the subgroup of 2 by 2 matrices over the complex number that are generated by these two matrices here. And you see they, well, for the Baumslag-Solitar group, we had instead of alpha here the q, but otherwise it's the same. So for the matrix group generated by these two matrices, the power word problem belongs to T-log time uniform TC0. Now for the case that the complex number alpha is algebraic, this result follows actually by the same arguments that I have shown you on the previous slide. But you may ask, what happens if alpha is a transcendental number? Well, that case is also easy. Namely, if alpha is transcendental, then this above group, this matrix group here, is isomorphic to the Reith product of two copies of the integer group. And for this Reith product, the power word problem was shown to be in T-log time uniform TC0 in an MFCS paper from last year. So this concludes the first half of this talk, and now I will pass to my co-author Georg Zetzsche.
Hi, I'm Georg Zetzsche, and I'm presenting our result on the knapsack problem. So the knapsack problem was introduced in 2014 by Myasnikov and co-authors, and it's the following problem. So you're given words W0 to WK over the generators of a group, and you want to know, are there exponents x1 to xk that you can place on the words W1 to WK so that you obtain the element represented by W0 in G. And while this problem was formally introduced in 2014, it has been looked at implicitly before that. So for example, in 1996, Babai and co-authors have shown that given non-singular commuting matrices over an algebraic number field, A1 to AK and B, deciding whether there are integer exponents, so that if you place those on A1 to AK in order to get B, then this problem is decidable in polynomial time. And if, however, the exponents range over the natural numbers, then the problem is NP complete. And after the seminal paper by Myasnikov, the knapsack problem has been looked at systematically for a number of groups. And I'd like to give you some overview of what's been obtained so far. And this is not a complete overview, but it's a selection of representative results. So the first result after Myasnikov was that there are finitely generated nilpotent groups where the knapsack problem is undecidable. And this is interesting because the word problem in those groups is always decidable. But the knapsack problem is in general undecidable. A general decidability result was then that for co-context-free groups, the problem is always decidable. A particular example of a finitely generated nilpotent group where the problem is decidable was then in the same paper shown to be the Heisenberg group. Myasnikov and others have already shown in their paper that for hyperbolic groups the problem is always decidable in polynomial time. And then a large group, a large class of groups where the problem is in NP is the class of virtually special groups. So the exact complexity then depends on the particular group, but for each of them the problem is in NP. And this year it was shown that for each free solvable group the problem is also in NP. But again, the exact complexity can be lower for individual of these groups. And the result in our paper here is that for Baumslag-Solitar groups BS1Q, the problem is NP complete. So for each Q, the problem is NP complete. And this is an unusual result in two respects. The first is that the problem is decidable, but the solution sets for these equations are not semilinear. And this is in contrast to almost all the results that we had before. So for co-context-free, for hyperbolic, for virtually special groups, and for free solvable groups, the solution sets are always semilinear. But here this is not the case. So for example, look at the following simple equation. T to the minus x, a t to the y should equal a to the z. Then if you look at solutions, then it's not hard to see that x and y have to be the same. So the solution set always contains the same number k in the first two coordinates. And if you recall the defining equation of the group, then you see that if you conjugate a with a t, then you get a to the q. So in other words, if you have a sequence of a's and you conjugate it with t, then you multiply that number by q. So if you do that k times, then you multiply the number of a's by q to the k. So this means it's not hard to show that then the third component has to be q to the k, which is clearly not a semilinear set. And the other aspect in which this is unusual is that minimal solutions can be doubly exponential. So usually the way to prove that knapsack is an NP is to first prove that if there is a solution, then there is a solution with at most exponential exponents. So where the numbers that you're looking for are at most exponential. And then you can guess a binary representation and show that the power word problem is solvable in polynomial time. This is what's been done, what had been done before. But in this case, we have examples of instances where the solutions are at least doubly exponential. So we cannot reduce to the power word problem. So how do we do it? So first of all, we use the representation as matrices. So as Marcus has said, you can look at BS1Q as a group of matrices, and then the matrices that you get are of the following shape. The topmost left entry is always a power of Q with an integer exponent, and the top right component is a rational number whose denominator is a power of Q. So a slightly larger set of numbers allowed for the top right component, and then the lower ones are 0 and 1. And it is also worth mentioning that for the groups BS1Q, even decidability of the knapsack problem was open. So decidability was known in a special case, namely if in the input instance, you know that this parameter L, so the exponent in the top left corner, is always non-zero. If that is the case, then Dudkin and Trier have a decision procedure. So what they did in this special case was they reduced it to the first order logic over an extension of Pressburg arithmetic, where you have the integers, addition and comparison, and also a function that maps n to q to the n. And Semenov in 1979 has shown that this is decidable. So what we do instead to get decidability in full generality, and also to get an NP upper bound, is we encode the problem in Büchi arithmetic. So Büchi arithmetic is first order logic over the structure integers with addition, comparison, and an additional function VQ. And this maps a number n to the largest power of q that divides n. And the key trick, as opposed to the Dutkin and Dyer approach, is to not introduce variables in the logic for the numbers x1 to xk. So what we do instead is we have variables for entries of these partial products. So instead of multiplying all the way up to k, w1 to xn to wk to xk, all the way up to k, we just multiply up to I, and we look at the matrices that we get there and formulate conditions on the entries of those matrices. So more specifically, for each fixed g, we construct a formula that expresses that if you multiply g to the matrix with entries a and b, then you get the matrix with entries c and d. And it turns out to suffice to do this, that it suffices to do this for variables over the integers. So this is pretty easy. This can already be done in Pressburger arithmetic because it's just addition and multiplication with constants. It gets more interesting if you do the second part, which says that A, B, C, and D have the property that there exists a number n, so that if you multiply g to the n to the matrix AB with entries AB, then you get the matrix with entries C and D. And this you can in fact express using this function VQ and a predicate that says a certain number is a power of q to the L. And you can imagine that if G has the shape described over here, then if you take a power of G, then you multiply this q to the L entry again and again, which requires you to say that a certain number is a power of q to the L. So we have this additional predicate. So what remains to do is to express this predicate pq to the L using VQ. And just doing this in first order logic is just standard methods. And that's because the set of numbers in Q-array representation that are powers of q to the L is a regular language. And well-known classic results about Büchi arithmetic state that this means it's expressible, this predicate is expressible using VQ. However, we would like to get a complexity upper bound, and for this we would like to use a result from last year by Gebhardt, Hase, and Worrell, which says that the sigma 1 fragment of Büchi arithmetic is NP complete. And using standard methods either has one of two problems. Either you use quantifier elimination to express being a power of q to the L, or you get an exponential blow-up. So a naive encoding would be to express being a power of q to the L using the function v, but with respect to a larger power of q. But then you have to, but if you want to do this with one exponent e, you have to choose e so that it is a multiple of each of the occurring numbers L, which would make e exponential. So then this would give a way too large number to still apply the result by Gebhardt, Hase, and Worrell. So what we do instead is we use an old trick to express being a power of q to the L by using being a power just of q. And this is as follows. It's not very difficult to show that a number x is a power of q to the L if and only if it is a power of q, and also q to the L minus 1 divides x minus 1. So that's an elementary factor proof, and this gives us a formula that just uses VQ and PQ, right? Because divisibility by this constant q to the L minus 1, so L is a number that is a small polynomial size number that we get from the input instance. This is just expressible in Pressburger arithmetic. And then the last step is to express being power of q just by VQ, which is trivial. You just say that VQ of x equals x. That says that x is that says exactly that x is a power of q. And so this gives us a small formula in the existential fragment of Büchi arithmetic, and therefore the NP upper bound. And the lower bound is just is very easy to do, just by a reduction from subset from a variant of subset sum. And that was it. Thank you.